This is level 2 of the CFA program, the topic on quantitative methods, and the learning module on extensions of multiple regression. I hope you're not tempted to think that this learning module, extensions of multiple regression, can be replaced by another title, complications of multiple regression. And in fact, there are 3 extensions and they're relatively simple. Let me tell you about them. The first one is a simple analysis of the data. The second one, we're going to add a non-quantitative independent variable or variables to our regression equation. We're going to call those dummy variables. And then our third extension, we're going to add a binary dependent variable on the left-hand side of the equal sign. And we're going to call that a logit or logistic model. So look at the LOSs here and you'll see what I'm saying. We're going to start with data analysis and we're going to have to define this term influence. Then we'll look at qualitative independent variables. I just referred to those as dummy variables. And then we're going to formulate a logistic regression model where the dependent variable is either a 0 or a 1. For example, a firm can either be bankrupt or it can't be bankrupt. So let's go ahead and start with this concept of an analysis of influence. And to begin, let me give you just a simple example here. Let's suppose that you collect monthly stock returns for an individual company like Johnson & Johnson or McDonald's. And you do that over a relatively smooth, let's say 3-year period where there's just regular old 2 or 3% economic growth. So think about these returns in an Excel spreadsheet. These are monthly returns, so sometimes you might have 1% and 0.9% and 1.1%. and 0.5% and maybe minus 2.2%. So you have these monthly returns. They're kind of coagulated. Is that a word? Coagulated together. But then let's go ahead and instead of collecting this data over a smooth economic 3-year period, let's suppose that we include the 2008 financial crisis, or we include the 3-year window that includes the reaction to COVID, or the 1987 stock market crash, or the Great Depression back in 1930s. So then what do you have? Well, you'll have a lot of returns that look similar to my first example. You'll have 1% and 0.8%. But then what will you have? Well, you might have a minus 4%. You might have a minus 8%. And I didn't give you an example where we have, tremendous economic growth. So what we're trying to do is we're trying to determine whether individual data points are different enough from the rest of them so that they can have an impact on the model's predictions. So then let's suppose we find this influential data point. And remember, the influential data point can be either contained in the independent variables or the dependent variable. And so look at our second arrow point there. Should they be removed from the data set? Let me tell you just a quick story. I remember when I was in my econometrics class, we used to have to do these kind of studies all the time. And I remember I asked the professor, I have this one data point that's way out there. Can I just throw it into the garbage can? And my professor, who was really a smart dude, he just shook his head and looked at me and said, Mr. Vorgin, you just don't get it. Now, the interesting thing is that this learning module points out the fact that when you collect the data, there might be errors in human entry into the Excel spreadsheet, or there might be errors in the data that you've already collected, that it's no fault of yours, but it's some other human error. Maybe there's a transposing of numbers. So there are times when you can remove from the data set. So that's really important. So look at that third arrow point there. An influential data point is one that has a significant effect. So this is going to skew our results. It's going to skew our inferences. So what we're going to do over the next couple of slides is try to figure out how do we determine what is an influence data point. 2 definitions to start off with there. A high leverage point is a data point with an extreme value on the right-hand side of the regression equation. These are one or more of the independent variables. So those high leverage points can have a relatively large influence on the fitted values. Now, if we were to remove this, then the regression line would change quite a bit. All right, that makes perfect sense. Now we're going to use this term called an outlier, is a point with a larger or smaller y value than the model would suggest. And so these could be too high or they could be too low. Now, the easiest way to do this is to go ahead and just plot your data. And, clearly you can see in the top left there, no outliers, no high leverage points, because there's the line, right? It's an upward sloping line, and all of the X and Y's, they fall, pretty close to the line. And then on the other three, you can see that there's outliers there, there's outliers there, there's a high leverage point over here. So these are very different data points. Think of the very first day of trading after the U.S. economy was shut down during COVID. These are outliers. These are high leverage data points. Now, it's relatively easy to do this if you have one X and one Y. One independent variable and then, of course, one dependent variable. But what if you have 100 of these? And then what if you have thousands of data points? And so if you go ahead and plot them, you can still do this, but you're going to get an ocular migraine headache trying to figure it out. So there's got to be a better way. And of course there is a better way. And we're going to call this thing, this first measure, leverage. And notice the notation there, H sub double I. It's a measure of the distance of an individual data point from the mean of the rest of the data. Now, I found it interesting that the learning module did not include a formula for leverage. And so I'm going to give you its input variables, and this may or may not help you answer a question on the exam. But what you do to compute this leverage is you start with 1 over n, n is the number of observations, and then you add a ratio. And in that ratio in the numerator is yi, right, each individual data point minus y hat or y bar, either way you look at it. So there's some distance there, and you divide that by a measure of the sum of the squares. And so if you remember our conversation about, quantitative methods and regression analysis from our previous slide decks, you'll kind of get what that leverage means. But I think that first diamond point is really a good definition to memorize. Now, the other thing you need to know is that leverage will always fall between 0 and 1. And so look down at the bottom gray box. There is a general rule of thumb for a potentially influential data point, and 3 times k plus 1, k is the number of independent variables, divided by n, n is the number of observations. You're going to need to memorize that general rule of thumb for the following reason. Now, if you watch my videos, you'll know that I generally wait until the very end to refer you back to the actual reading and to look at the questions at the end of the learning module. But I'm going to do this right now. There are 12 questions, 2 item sets at the end of this learning objective, and they cover everything that we're going to do in this slide deck. The very first question is using this general rule of thumb. So there's a quick example at the bottom, 50 observations, 10 independent variables. So any observation with a leverage greater than, 0.66 would be considered potentially influential. So here's the thing. You're not going to have to compute that leverage, but you'll have to compute the general rule of thumb and then compare it. Think of it as kind of like looking at critical values versus the observed statistic that you compute from the model. Now, speaking of statistics, back here and this leverage is really just kind of a formalized way of looking at, and let me go back here real quickly too, a formalized way of looking at these graphs. But as you can imagine, there are econometricians out there who have said, you know what, if we're going to do this the proper way, we need to come up with some kind of a test statistic. So this is the studentized residual. So there's the formula there in the very middle of the slide deck. There's the studentized T. And all we're going to do is we're going to take the ratio of the residuals and divide that by the standard deviation of the residuals. I'm not sure you need to know that equation on the right-hand side. In fact, I'm guessing and betting that you don't. But let me tell you how the studentized t residual works. What you do is you estimate the regression parameters using all of the data points. And then you just go ahead and, let's suppose you have 100 observations. You run the regression by eliminating the first one. So you have 99. Then you run the regression again with eliminating the second one. You have 99. So you do that all of those times if you have 100 observations. And there's the t. Now, the great news for you guys, and I'm going to go ahead and refer you once again to the vignettes at the end of the learning module. What the Institute does is that it gives you every studentized t for the observations that are in that particular model. So you almost certainly won't have to calculate that. I mean, in the very, very strangest sense, maybe they'll give you the residuals in the numerator, maybe they'll give you the standard deviation in the denominator, but I'm guessing that because the end of the learning module examples give you the studentized t, that you probably won't have to do it. So then the question becomes, well, how do we know if that's significant or not? Well, we have some general rules here. If that studentized residual is greater than 3, then the observation will be deemed an outlier. But you can also go ahead and look this number up on the table. That critical value of the test statistic is going to be with n minus k minus 2. That's really our degrees of freedom for multiple regression. So you have two ways to do this studentized residual. And that's important to remember. Back here, let me go back here. So with leverage, you just have this kind of first rule of thumb. With the studentized, you have a general rule of thumb, generally speaking, but then you also can look this number up on a table. Now, of course, you're probably thinking along the lines, is there another test out there as well? And of course there is. This is Cook's distance, which is a measure of how much the estimates of the regression coefficients would change if that observation were removed from the data set. So what you can do with the Cook's distance is that you can do the same thing that you did before. You can, what I say earlier, you have 100 data points, you can go ahead and remove one and recalculate Cook's distance for every one of those observations. Or you could combine that with your analysis of the graphs, and you could say, oh, these 87 are pretty good, but these 13 are not, so let's go ahead and take a look at those 13. Now, clearly, if you look at that equation in the middle of the slide, you're going to go ahead and scratch your head and say, you know what, Jim, do I really need to memorize that thing? And I'm going to go ahead and go out on a big limb and say probably not, and I'll tell you why not, and you'll prove this to yourself. When you go to that question at the end of this learning module, you'll see that in the vignette, the Institute gives you, and let me go back here, they give you studentized t's, and then they give you the Cook's distance for all of the observations. So I'm guessing they're gonna do that as well. But just for kicks and giggles, like my cousin says, let's go ahead and look at the numerator, right? We're taking each individual y minus, the y hat, which is, what those things, how well this model fits the data. We're gonna square that and divided by the mean square of error, which, remember, I said to you, we had some kind of measure of the sum of the squared deviations for our measure of leverage, but there's that measure of leverage over on the right-hand side. So I wouldn't worry too much about this equation. But let's go ahead and interpret this. Let's just skip down to the bottom gray box here. If that Cook's distance is greater than 0.5, there might be further investigation needed. And it's interesting that the learning module suggests then, if this has a potential for being influential, go back and look at the data set and make sure that you entered it correctly. For example, you entered 13 instead of 31. I mean, that makes perfect sense. But if it's greater than 1, highly likely to be influential. And if it's greater than 2 times the square root of k over n, it's also highly likely to be influential. So make sure make sure with Cook that you take a look at both of those conditions down there, greater than 1 or greater than 2 times k over n. All right, so that was our first extension. Our second extension is to consider qualitative independent variables. So let me give you another example here before we move to this particular slide. Let's suppose that our dependent variable is the actual score earned by a CFA candidate on the exam. Now, we don't know what that actual score is when we get our results, but the institute knows what that is. So let's suppose that we come up with a model that says, what are our independent variables? So let's suppose that we say something like hours studied. That sounds like a good one. How about a measure of skill, like we could do maybe the IQ of the candidate, or maybe the undergraduate GPA of the candidate, or some measure of skill. You don't want to do both of those because then you would probably have multi-collinearity. And then let's add some 0, 1 variables, right? Let's go ahead and say, all right, let's add a variable to determine whether or not if a candidate has a master's degree is significant in predicting CFA test scores. So that's a yes or no, right? A dummy variable, 1 if the condition is met, 1 if the candidate has a master's degree, 0 if not. How about this one? How about selfishly, I say, how about let's add another variable, 1 if the candidate watched at least 100 hours of my videos, and 0 if not. And then let's throw some other one in here. Don't scoff before you hear this because it might have some value. How about we say we add a third dummy variable, 1 if the candidate ate a full breakfast before taking the exam, and 0 if the candidate showed up on an empty stomach. Hey, that makes kind of sense. Now look at some of the examples we have at the bottom, right? Reflect an inherent property of the data location, over there versus over there. 0 to represent pre-2007 crisis, 1 for post-2007 crisis. 1 if the debt ratio is less than 2, 0 if the debt ratio is greater than 2. So do you see how you can take all of these qualitative variables and transform them into a quantitative variable? I mean, it would be ideal if we could just come up with some rate of transformation, rate of perfect transformation from a qualitative variable into a quantitative variable, and then we wouldn't have to worry about these kinds of extensions of the multiple regression model. But of course, we can't. I mean, there's no way that you can say something like, all right, how do you measure whether a candidate ate breakfast or not? It's either yes or no, and that's pretty much the extent of it. I don't know, I guess you could probably come up with some scale, like a 1 if the candidate had cereal, 2 if the candidate had apples, 3 if the candidate had oatmeal. I don't know. I'm just babbling on here. All right, so there are 3 different kinds of dummy variables. There's an intercept dummy, and the best way to understand this is to take a look at the graph over on the side. So think about this. If you run a regular old regression, you're going to get an intercept term. And that intercept, of course, can be above or below the origin. So what we're going to do is we're going to add an intercept dummy, in which case that's going to either move significantly up or significantly down. If you're following along, you could probably predict what the next dummy is going to be. It's a slope dummy. So what we're going to do is add a slope dummy to see if the slope of the regression line changes, from like this to like that, or some other way. How about if it changes from upward sloping to downward sloping? Boy, then that's a significant slope dummy. And then what we can do is we can combine those two. We can add combination dummies that both increase or decrease the intercept on the vertical axis, and then they influence the slope. Now, the reading does exactly what we're showing you here in the slide deck. And I don't want to go through all those equations there because I think it might bog you down in terms of being able to answer a question. So we, of course, have come up with a good example. You ready for this? 5 key characteristics to affect mutual fund returns. So expense ratio, that makes sense, right? Assets under management. Let's take the natural log. So instead of having, this much variability, we only have this much variability. Management experience in years, and dummy variables to denote fund style. So we have growth, we have value, and we have blend. So we have three different styles. So what we're going to do is we're going to have 3 minus 1 dummy variables. There's that things to note there. All right, ready? So look at the equation. Fund returns is dummy 1 is value, dummy 2 is blend. We don't need a dummy for growth because that's going to be reflected in the difference in the intercept. And then we have a slope coefficient for expense ratio, 1 for assets under management, and 1 for management experience. So just make sure you understand this. Let's go through those teardrop points down at the bottom. The dummy variable value takes on 1 if the fund's preferred style is value, 0 if not. The dummy variable blend takes on 1 if the fund's preferred style is blend, 0 if it's not. Now look at that purple teardrop point. The base or the control category is growth, for which we do not need a dummy because we're going to see what happens to the slope. All right, so here's the regression output. There are the coefficients going down that first column, standard errors, just like we did in that previous slide deck. And then the test statistics, well, you probably could predict with those standard errors that look to be relatively small there, the test statistics, they have to be super big. And of course, I think I've said this to you in previous recordings, this is, you don't need to learn this from me. I mean, clearly we're going to look these numbers up on the table and compare them to their critical value, but just kind of a first look, you just compare them to an absolute value of 2. And all of these are greater than absolute values of 2, so they're all going to be statistically significant. So what can we conclude? We can conclude this is probably a good model, right? Probably an excellent model. Later on, we're going to look at the f-statistic, and the f-statistic, that test is going to be super. I'm not sure this is a statistics term. It's going to be super statistically significant. And then, of course, with such high t-stats, you're going to have p-values that are essentially 0. Some regression outputs insist on giving you the e to the minus over there. I don't even have any idea what e to the minus 221. I wouldn't even want to try to move my decimal place 221 to the left or to the right. I don't even think I'd want to move them 32. What's the lowest one there? 22. So those p-values are essentially 0. So let's go ahead and work through a couple of the, kind of logical conclusions that we learned in the previous learning module, and then we'll go ahead and specifically talk about the dummies. So let's not forget about our 3 regular old quantitative independent variables. So the fund returns are negatively related to expenses. That makes perfect sense, but positively related to assets under management and management experience. So those 3 variables are significant. So what kind of conclusions could we make here? What we could say is find mutual funds that have low expense ratios, find mutual funds in which the manager has, pick a year, 8 or 10 or 15 years of experience, and then find larger funds, right? That makes perfect sense. All right, how about the dummy variables? So let's go ahead and look down at the bottom. There's the value dummy, 2.687, and this is a super important interpretation. Look at that little cartoon box that we have. This is exactly one of the questions at the end of the learning module. So the value dummy tells us that those value funds deliver returns that exceed the growth base, that exceed the growth, right, by 2.687%. Look down on the bottom right. The blend funds deliver an average of returns in excess of the growth category by 0.558%. Oh, so this tells us a lot. And you see how we only need to have n minus 1 dummy variables, right? So we've got the 2.687 and the 0.558. So what does this tell us? This tells us that value and blend are way better than growth funds, and they're better by those amounts in the blue and in the green. Now, feel free to say, hey, Jim, thank you for encouraging me at the beginning of this, because I really thought this reading was going to be on let's complicate life in multiple regression. But you see how valuable this dummy stuff is. I mean, look at how cool it is to be able to make those blue and green conclusions. So back to the intercept term, 2.85% is unexplained by the independent variables in the model. And we can attribute that, at least partially, to growth. Now, I said to you just a moment ago, let's go ahead and do the f-test. We don't need to do the f-test, but if we want to do the f-test, we could. Look at the f. It's 623, and I'm pretty sure I don't really care what kind of a table you look on. Yeah, let's do 5 degrees of freedom in the numerator and 120 degrees of freedom in the denominator. What do we get? 2.29, so we knew that. We knew that beforehand. All right, so let's go ahead and look at the same model, but let's introduce a slope dummy. So does our slope go from here to here, or does it go from here to here? Everybody see what we're trying to do? Look at the equation down at the bottom. We're going to go ahead and say value and blend, they're still there. Expense ratio, assets, experience, they're still there. But now, notice what we're going to do. We're going to take the experience times value, and we're going to take the experience times blend. So look at what our hypothesis is. We want to investigate whether management experience impacts the returns differently based on the style of the fund. In other words, if I'm a 10-year experienced manager of a value fund, maybe I'm way better than a 10-year experienced manager in a blended fund. Oh my gosh, you see how cool this extension of the model is. So let's go ahead and look at the results again. Notice that those standard errors are still relatively small, and the test statistics, they're probably going to stay significant. Of course they do, all the way down to our slope dummies. Now look at the experience times value. That t-stat is only 546, right? And the p-value is 0.55. Oh, wow. So what did we find? We found that that's not too important to the model, but the experience with the blend is statistically significant. So, boy, we can make some super conclusions here. Oh, by the way, look at that p-value down there. It's not e to the minus 221. It's only 1.5. All right, so let's do this again here. Statistically significant slope coefficient, right? So our indication was that management experience was an important variable. But now, when we interact that with value, it is not significant at the 5% level, but it is significant when we combine that with blend. So what we can do here, you ready for this? This is so cool. The extra annual return with each additional year of age. Oh my gosh, we'll just take the 55 and add it to the 0128, and we can say, boy, 6.8% is the extra added return. Now, of course, we have to be super careful with the units, so we probably didn't know this when we read the vignette in this one, but clearly the Institute would convey this. So an extra annual return, extra additional year. So there are the 2 units. Now we can also make a comment about blend. There's 1.85%. Now let's go back to my example with the score on the CFA exam. But instead of our dependent variable being 22%, 43%, and 75%, and 85%, let's just suppose our dependent variable is Either you pass or you don't, either a 0 or a 1. So essentially what we're going to do is we're going to take that dummy variable on the right-hand side of the model and just throw it over onto the left-hand side of the model. Everybody get that? Now, of course, we can't run a regression analysis with a 0 or 1 for a variety of reasons, but most of the reasons center around the fact that the resulting beta coefficients probably are going to end up being greater than 1 or maybe negative in fact. So what we need to do is we need to transform that data, and I'll show you how to do that here in just a second. All right, so look at the second embedded bullet point. The goal of this logistic regression model is to find the best fitting model to describe that relationship, right? So there we go, binary, 0 or 1. And here's an example that we're going to work through in this slide deck. So we're going to say, hey, we're going to predict whether a customer will default. So you either default or you don't default based on how much you owe, customer's balance, and the customer's debt to income ratio. Well, look at that third embedded point there. So to model the dependent variable using a linear model, we need to transform the above equation into a logit function. And so that's what we're going to do. We're going to take that probability, that p there, and we're going to divide it by 1 minus p and then take the log. So the Institute is probably not going to ask you to do all that. But it's important to know that the left-hand side, the dependent variable, is not a 0 or a 1. It's that thing right there. Now, we can't use the regular old least squares regression. We have to use what's known as the maximum likelihood method. That's the second to last embedded bullet point. Coefficients give the expected change in the log of the odds for a 1 unit change in the variable. And I'm going to go ahead and repeat what I said just a second ago. Make sure that you're aware of whatever that 1 unit change is in the variable. So let me swing back up to the second embedded bullet point. That thing looks like it's a monstrosity, and maybe it is, but all we're doing is trying to figure out a probability, p there, right? And what we're going to do is use our exponent function. And so we're just taking the exponent function, and then there's our model. Remember now we have x1 and x2, so that's the credit card balance and the debt to income ratio. And then we're going to divide that by 1 plus the exponent of that same model. So that's going to give us some probability, and that's going to be the left-hand side of our equal sign in the regression model. All right, so here are the results of this model. Remember, let me just say it again. Credit card balance is x1 and debt to income ratio is x2. So there's the coefficient. There are the standard errors. And when you use this maximum likelihood, you have to use the z instead of the t. And there are p-values. So the intercept is significant. The balance is significant. But the debt to income ratio is not, p-value of 0.711. Now, going back to the end of the learning module questions, what follows is the Institute is going to say, all right, here's the model. Well, they'll give you a model. So here's the model. Here is the maximum likelihood output. And then complete the table. All right, so what I want you to do is I want you to get out your calculator. I'm going to do mine here as well. I want you to do this with me. You ready? I had to take my glasses off because, as you know, those of you who've been paying attention know that I can't see. So there's let's do the balance coefficient. Let's do that one. So it's 0.0055 in your calculator, and then hit your e to the x button, and you get 1.005. So the Institute, they might ask you for those odds. So they might ask you for, and if you have to do 2.7536 times 10 to the minus 5, if you got to put all those decimals, if they give you a minus 22 or a minus 200, I would raise my hand and say, I'm protesting this question here. So you get the 1.005, but then the probability over there on the right-hand side, that's probably an even better question. So we're going to take the odds. So you have 1.055 in your calculator and divide that by 1 plus the odds. So do divided by 2.0055, and that gives you the 5014. And that pretty much summarizes what the Institute does at the end of this reading for for these particular questions. So there's the model there. Let's go ahead and review some of the conclusions that we can make. All right, the intercept, notice we have the word negligible in there, right? So that's a very, very low probability. The balance, however, a one unit increase in the credit card balance. So you need to make sure, is that a $1 increase? Is it a 1% increase? So the Institute will have to tell you that in the question stem or the vignette. It increases the default probability by about 50%. And this is important, holding the other variables constant. For debt to income ratio, it's about the same, 50%, right? So a 1 unit increase in debt to income ratio increases the default probability by 50%. And then the very last question, number 12, at the end of this learning module, they ask you to determine the probability of default, and they want you to use this model this equation down at the bottom. And that looks super difficult, but I promise you that it's not. So there's your homework assignment. Go to the very last question, and you'll look at that one, and you'll say, you know what, Jim? That's super easy stuff. So we only have 3 learning outcome statements here, but tons and tons of questions. So I would be prepared. And if you go through those 12 questions at the end of the learning module, and then couple that with all the questions that we have, independently and in our mock exams, you ought to be able to hit those 3 learning outcome statements. So thank you for watching, and good luck studying.